Okay, this is solving density problems. We need our calculator, the density equation, and some rules. So we have three rules here. Make lists of variables, isolate for our unknown variable, and then include units as we solve. I'm going to take some time to write those down. Also, we're going to sometimes multiply by a reciprocal. And we're going to use that in example 1. I'm going to reference you back to how you did division problems with fractions. Here we have 5 halves divided by 3 sevenths. We kept the top the same. We changed the sign, so instead of division we went to multiplication. And we took the reciprocal of the bottom, so instead of 3 sevenths we have 7 thirds. And then we multiplied. If you want, this looks a lot like dimensional analysis that we've been doing. So we could put bars here. But ultimately we have 5 times 7, 35. And 2 times 3, 6. And we could simplify. Okay, we're going to use that in example 1. We've identified our density as 7.2 grams per centimeter cubed. Volume is what we're looking for. And mass is 36 grams. We start with our density equation. D equals m over v. And notice we haven't isolated for volume yet. We need to get v by itself. So I'm going to do a little bit of work here. Multiply both sides by v. So the v's cancel. That leaves me with v times d equals m. Now we're going to divide both sides by d to isolate v. So v is mass divided by density. So now we have that equation. We're going to come back here. Instead of mass, we're going to plug in 36 grams. And then we're going to divide that by the density, which is 7.2 grams per centimeter cubed. Because I have a fraction on the bottom, I'm going to turn the top into a fraction as well. So I'm going to call that 36 over 1. That's just personal preference. So now I'm in a situation where I can use reciprocal multiplication to solve this division problem. So I'm going to keep the top the same. 36 grams over 1. I'm going to multiply. And I'm going to flip the bottom. And notice the units now. I'm going to put 1 centimeter cubed up on top and 7.2 grams down on the bottom. Now we've got a situation where grams cancel out. The only unit we have left is centimeters cubed, and we're in a dimensional analysis situation like we've been working on. We're going to go for our volume then. We're going to go 36 divided by 7.2. Which is 5. In terms of significant figures, there were 2 significant figures in 36 and 2 in 7.2. So we're going to say 5.0 centimeters cubed. And we're done. Example of the use of reciprocal multiplication. We isolated volume in our original density equation. So we started here. We did some work to get v by itself, and then we plugged in and solved. Second one's quite a bit simpler. Again, we have our list of variables. In this case, we're asking for d. Fortunately, d has already been isolated in our original equation. We have a mass and a volume. We can plug straight into those two things. So we can say d equals mass 12.5 grams divided by volume 9.5 milliliters. And now we're ready to go. So we take our calculator. We get 1.315. There are 3 significant figures in 12.5 and 2 in 9.5, so our answer is going to have 2. We take the 1 and the 3. The 1 does not round the 3, so our answer is 1.3. So our density is 1.3 grams per milliliter. This object would sink in water because its density is greater than 1. For our last example, we're going to solve for a mass situation, and we're going to use a couple conversion factors here in our work. But first we're going to isolate our variable, so d equals m over v. We determined that we're looking for m, so we're going to multiply by v on both sides. And so we're left with mass equals volume multiplied by density. Okay. Or I could say mass equals density multiplied by volume. Wouldn't matter. So I come down here, put my density in first, 5.8 grams per centimeter cubed. Mass should be in grams, so I'm looking to ultimately cancel centimeters cubed. I have a problem because my volume is in liters. So instead of just dropping in the 2.4 liters there, I'm going to realize that and get those liters into centimeters cubed prior to completing my problem. So here we go with some dimensional analysis and conversion factors. We want to go from liters over to centimeters cubed. Again, pause the video at times if you need to stop and think about it. We're going to go first from liters into milliliters. So we're going to put liters on the bottom, milliliters on top. My numbers are 1,000 milliliters in 1 liter. Placeholder 1 right there. So liters cancel. We have milliliters. We've got one more step to get to centimeters cubed. Again, we're going to cancel milliliters and we're going to go to centimeters cubed. We know that there is 1 milliliter in 1 centimeter cubed. Effectively, milliliters cancel. We have 2.4 multiplied by 1,000, which is 2,400 centimeters cubed. So that is a better volume to throw into our m equals d times v equation. So we're going to go ahead and do that right now. We're going to multiply our 5.8 times 2,400 centimeters cubed. Again, this resembles or looks a lot like the dimensional analysis stuff that we've been doing. I'm going to go ahead and put the bars on it. And 2,400 over 1. Anytime there's a unit on the bottom, if you'd like to put a 1 there, you're welcome to. This literally means 5.8 grams over 1 centimeter cubed. Centimeters cubed cancel out. The only unit we have left is in grams. We're looking for mass, and we know that's in grams, so we're in good shape. This becomes a multiplication problem, 5.8 multiplied by 2,400. $13,920, and that's grams. In terms of significant figures, both values in this problem, both the 5.8 had 2 significant figures, as well as the original 2.4. So our answer should have 2 significant figures. So we take the 1 and the 3 and we ask ourselves, does the 9 round the 3? Yes, it does. So this becomes not 14, but 14,000 grams. And if we wanted to put that into scientific notation, we would say 1.4 times 10 to the 3 times 10 to the 4th grams. We're going to be doing this a lot in chemistry, where we take original formulas like D equals M over V, and we manipulate variables and solve for unknowns. So in these examples, we isolated V and solved for it. We isolated D and solved for it. And we isolated M and solved for it.